Hey, intro to statistics. We're not. You could spend your whole career in statistics. People do. They're called statisticians. We're gonna spend a few minutes in statistics. We can't become experts, but it's worthwhile to not be completely illiterate in the subject. At least it's good to know enough that you can understand what claims a statistic is or is not making, and have some clue as to whether it's reliable or not. So, when we first introduced induction, it was reasoning by analogy. Statistics is more reasoning by analogy. But with the first pass at induction, we reasoned by analogy in a categorical manner. I saw one A had property B. So I think that all A's have property B. What if you get a counterexample? Doesn't work. So no A's have property B? Wait a minute, but the first one I saw is a counterexample to that. What percentage of A's have property B? When you're dealing with things that aren't all or nothing, then you've got to apply analog, fuzzy logic. You got to make not a categorical induction, but a statistical induction. So, in a statistical induction, you see that some percentage of A's that you can see have property B. But you know that there's a real lot of A's out there that you know they're out there, but you don't see them. And you're wondering, out of all the A's out there, how many of them have property B? And you extrapolate from what you see in your little sample, A's you can see, to make a guess about all the A's out there. How many of them have property B? That's a statistical generalization. Okay, let's do an example. Let's say 65% of the adult citizens of France who were polled approve of the job that Sarkozy is doing as president. Therefore, 65% of French adults approve of Sarkozy. That is a statistical generalization. They're extrapolating from people they polled to everyone in France. Whether it's a good generalization or not, we'll get into in a little while. First, we identified it as a statistical generalization. And a few words of vocab. There's three important pieces of a statistic. The relevant property. What are we trying to talk about? Property B that some percentage of A's have. The approval rating of Sarkozy. Those are features, properties. Those are the issue that the topic that the statistic is trying to give more info about. And the statistic tries to give more info. The statistic deals with two groups that may or may not have that property. One's a big group, one's a small group. The big group is called the population. Like, we really want to know what all of France thinks about Sarkozy. But it would be way too much work to ask every single person in France. So we don't measure the whole population, it would just be too much work. We take a sample. So as opposed to, we want to know about the whole population, but we just take a sample. So relevant property, population, and sample. And whether a statistic is good or not depends mostly on what population we try to apply the sample to, and whether that sample is a representative cross-section of the population. In other words, is it a biased sample, or does the sample accurately, or is the sample a true microcosm of the population? If the sample is indeed a true microcosm of the population, then, little randomness aside, features we see in that sample will apply correctly to the whole population. If not, then we'd call it a biased sample. Okay, so generally you'd hope that a sample's representative. You probably want an example of a biased sample. Okay, so different political question. Here's a famous example. So it's 1936 in America. They have an election coming up. So some magazine does a poll to ask people who they think is going to win, or who they're going to vote for. And whoever gets the most votes win. So they ask like 1,000 people, not all of America, but still, it's a lot of people. And they're making the statistical generalization that whichever candidate gets the most votes out of that sample of 1,000 will probably be the same guy who gets the most votes in the real whole country election. So they call up 1,000 people. Hey, who are you going to vote for? 1,000 people later, they have some results. They think that Alf Landon is going to beat Roosevelt by a lot. Turns out that actually Roosevelt beats Landon by a lot. And so they're like, what happened? Why was our survey wrong? What was wrong with us as statisticians? What was wrong was that they had a biased sample. Remember, it's the year 1936. Hardly anyone has telephones. Only very rich people at that time had phones. So if you dial the phone number, you are guaranteed that a rich person is going to pick up, because no poor people own telephones at this time. So what their 1,000 people was a representative sample of was what the rich people in America thought, who the rich people were going to vote for. And if you only asked, hey, who did the rich people vote for? Yeah, the rich people overwhelmingly voted for Landon and not for Roosevelt. The sample was a representative sample of what the rich thought. However, the survey designers failed to take into account the fact that only rich people had phones at this time. So they misidentified their population. They tried to extrapolate a sample of rich people to the entire United States, which includes a lot of poor people. And when they did that, obviously they had a mismatch. Their prediction was wrong. You could say that they tried to extrapolate too far. They applied their statistic to a non-matching population. You could say that. More often, though, people phrase it the other way around, saying that their sample was biased, like leave the population alone and say that their sample had something wrong with it. Actually, either way works fine. But you've got to watch out for that. You've got to make sure that your sample is a true microcosm of whatever big population you're going to try to apply your sample to. If they're not matching, if the sample isn't representative, then your statistical generalizations are probably going to be pretty inaccurate. There's two more ways that statistics can be hard. One is biased questions. Like with the previous example, hey, who are you going to vote for? Landon or Roosevelt? That's pretty straightforward. It doesn't really lead the person at all. But sometimes questions in surveys are not so easy to phrase well. Sometimes how you ask a question will affect how people answer. Like, I could ask, do you support affirmative action? Or I could ask, do you support reserving spots at universities for different races? Technically, they're the same thing. One sounds weird and unfair. One sounds like it's some good words. Affirmative action. One sounds good. One sort of sounds weird or bad. So if someone's lazy and doesn't do the work to ask for a stipulated definition or research the definition of the terms, they might just guess based on whether the word sounds good or sounds bad. Connotation arithmetic. And a lot of people are lazy and just sort of guess. And so a lot of the time survey results will be different depending on whether when you ask a question about a thing, use happy words or frowny words. Really, it shouldn't be that way. Really, people should do a better job of figuring out what the words in a question mean before giving an answer to a survey, but a lot of people don't. And it's hard to know whether your survey respondent actually understands the issue or not. Usually they just check off a box or say yes or no. It's hard to make sure that you don't have idiots in your sample. And really, if you're surveying the whole population does have a lot of idiots. So if you exclude idiots from your survey, good luck making a statistical generalization to the whole idiot-laden population. So phrasing questions well is hard. The connotations of words matter, and it's hard to get around that. The last thing that really matters in survey design is sample size. Even if your sample is representative, if your sample's too small, that's a problem. Like with even the bad telephone survey, they still called like 1,000 people. They called a lot of people. The bigger your sample is, well, if it's a biased sample, size isn't gonna help until you sample like the entire population. So A bigger sample won't really overcome bias, but even if your sample isn't biased, it's still possible for your sample to be too small. And if your sample's too small, then randomness becomes a big problem. And Plato and Hume were right. You can't rely on real world stuff because it's too messy and random. That's why we need big sample sizes. Let's look at the complete opposite. Let's say I'm doing a survey of coin tosses. I'm flipping a coin, and I want to know how much of the time does it land on heads, and how much of the time does it land on tails. Well, we know the answer. It's like 50-50. Maybe like 49-51 if like one side of the coin has like a fat guy on it and you have more metal on that side, but still like really close to 50-50. So I do a experiment. Or a survey of one coin toss. Every time the coin lands, it never lands half heads, half tails. It never really lands at its side. It always lands all heads or all tails. So if I just do a one coin toss experiment, I don't know whether it's going to be all heads or all tails, but it's going to be all one of them, which is as far as you can get from the truth of 50-50. If I flip the coin more times, I'm going to get some heads, going to get some tails, and the more and more I flip it, the closer we're going to get to about 50-50. But if I only flip it one time, I'm guaranteed to be off by 50%, either 0 or 100. So you need your sample size to be big enough. Defining what big enough is and what sufficient sample size or study power are, that would require some real math and statistics. So we're not going to go into the numbers there. We'll stop with the general idea that a sample needs to be big enough. If you really are doing a survey and need to know what big enough is, call a professional statistician. There are professionals. They can tell you quickly. But moreover, a study needs to avoid bias, both in how it asks its questions and in who it asks its questions to. Because if your sample isn't a representative slice of the population, then you run into errors when you apply your results of your survey to that population. Like when the magazine asked about a popular election and just asked rich people who own telephones. They got a good survey of what the rich people thought, but then mislabeled it as a survey of what all people thought, and what rich people thought and what most people thought weren't the same thing. They ended up being wrong. It takes a lot of sample size, bit of effort, and a lot of thinking beforehand to correctly apply gambling math and thereby not lead yourself astray when you're trying to do statistics. Statistics is hard. That's probably one reason why it was only invented relatively recently in history. And for most of history, like before Galileo, people really didn't trust making conclusions from observing the natural world. People really didn't trust science. They trusted math and logic, but not science. However, you can only do so much with pure math. You can do a lot more if you apply math and logic to the real world. If you need examples of that, just look at any scientific discovery or advancement that we have gotten from science. Because applying critical thinking, logic, and math to real world observation is the recipe for science, which we'll talk about a little next time. See.